Classically, in game theory, we study games with two players who have opposite objectives, such as chess or tic-tac-toe. In such games, we are used to ask questions such as, does this player have a winning strategy against all the possible strategies of the opponent? For example, in this game, if player square goes to the right, he is sure to win, while if he goes to the left, player circle could make him lose. But such a solution concept does no longer make sense in games in which there are several players with objectives that are not necessarily in contradiction with each other. Consider this game in which both players have the same objective. They both win if they both go to the left. Then we'd like a solution concept that covers the natural behaviors in such a game. Both players go left. Those behaviors form a Nash equilibrium, that is, a strategy profile in which no player can improve their payoff by deviating alone from their strategy. Problem, there is another Nash equilibrium in this game. If both players always go right, they need to both deviate to win. For player circle, planning to go from B to E is what we call a non-credible threat, and it is what the stronger notion of subgame perfect equilibrium forbids. The question is now, given a game, how do we decide whether there exists a subgame perfect equilibrium or whether there exists one that satisfies some constraint, especially about the payoffs? That problem has been solved, for example, in parity games, or more recently in quantitative reachability games. But it was still an open question in mean payoff games. This is the problem to which we propose a solution.
Hello, I'm Nudula from University Libre de Brussels, and at Concur 2021, I will be talking about fragility and robustness of adversarial Stackelberg games. Stackelberg games have two players, the leader and the follower. The leader moves first by announcing the strategy which he is going to play. The follower responds by playing an optimal best response. In this work, we assume that the follower is adversarial, that is, he would try to minimize the payoff of the leader whenever possible. We consider here a matrix game, and we see that the best strategy for the leader under the assumption of an adversarial follower is to choose to play strategy 1. We see that the leader here receives a payoff of 100, and we call this the adversarial Stackelberg value of the game. However, if we see that the values are off by even 10%, that is if there are perturbations in the game, the same strategy of the leader would give us drastically different values. That is, here the payoff of the leader would be 0. We realize that ASV is fragile. To create a more robust notion of the ASV, we assume that the follower plays an epsilon optimal best response instead of a best response. Under this assumption, we state that the strategy chosen by the leader gives us some sort of performance guarantees in any perturbed game. We call this the epsilon adversarial Stackelberg value of the game. We show that the epsilon adversarial Stackelberg value is robust against perturbations in games. In this work, we look at the threshold problem and how to compute the epsilon adversarial Stackelberg value and show that there's a strategy to always achieve this.
Hello, let me give a short summary of my paper. We study infinite duration games on finite directed grounds. Famous examples of such games are parity games, mean payoff games, and discounted games that all have prominent applications in, say, logic and algorithm design. And also all these games share a nice property of positional determinacy, which basically means that for both players in this game, it is sufficient to play optimally, it is sufficient to use the simplest kind of strategies in these games, namely positional ones. And we are interested in a systematic study of positional determinacy, namely like given a payoff function, an arbitrary payoff function, we want to be able to find out whether this payoff function induces a positionally determined game. In this paper, we restrict ourselves to a subclass of continuous payoff functions that in particular include discounted games, but not parity and mean payoff games. And our main result is a very simple to state characterization of continuous payoff functions that induce positionally determined games. We actually proved it in 3 different ways, which gives us some additional structural and also algorithmic result regarding this class of payoffs. That's it. Thank you.